Hi, everyone. Welcome to another episode of the Common Lisp Study Group. I'm your host, Ron Baden with Atlanta Functional Programming. Today, we are going to be continuing our discussion of paradigms of artificial intelligence programming, case studies in Common Lisp by Peter Norvig. We are beginning our actual journey today with what Dr. Norvig calls classical artificial intelligence problems. Now, these are problems for those of you who are just coming into the field who have probably followed along with the machine learning innovations of the last 10 years are problems that are more or less fall into the category of what most people would have considered traditional AI prior to the kind of renaissance of machine learning and deep learning and reinforcement learning of the last decade. Now, some of these problems include uh, concepts like planning strategies, expert systems, where essentially you're dealing with the idea of satisfaction of goals and approaches to actually solving these kinds of general task management sort of like issues. The particular one that we are going to be covering to begin our discussions and case studies is chapter 4, which covers the general problem solver. The general problem solver was first proposed and actually created by Alan Newell and Herb Simon in the 50s, prior to, I believe, the actual invention of Lisp in 1958. It was actually, I think, 57, according to the book, that the implementation of general problem solver was created. This is the first AI program that was actually created, and surprisingly, from most people, I'm sure, this was created in the predecessor that I mentioned to Lisp, which was Information Processing Language, or IPL. This was created by the folks over at Dartmouth in the 50s, and it was used to actually create the first version of GPS, the general problem solver. The notion of the general problem solver is actually pretty simple. The question that was proposed by, I believe it was actually Dr. Newell and Simon in their discussion of it. At least I'm going off of what the books mentioned is the idea of the fact that you are dealing with. Hold on, let me pull up my notes here since I actually wrote this up. It was uh, it was attempted to create a program that could solve any problem given a suitable description of that problem. Okay, and what that meant is um, if I'm able to take just some sort of general natural language problem, like let's say the example that was given to um, in the book was driving your son to school. There might be different constraints to actually go and actually attempt that task. So, like for example, your car may need a battery. You have money, but you need to go look up the mechanic's phone number somehow, and then be able to call the mechanic, go to the shop, buy the battery, have the shop install the battery, and then the car is now working. So now you can actually go drive your son to school, and your son should be at home at the time that you are trying to drive him to school. So that's a very vague description on how one might end up trying to encompass and have the general problem solver solve it. Now, obviously, I'm not as precise of what than the description that was described in the book, but I'm giving you kind of the vague idea on what I understood of how this kind of description worked. Now, the notion of what the problem solver was supposed to do is take the suitable description and what knowledge you give it. So there has to be a representation of the constraints that you're trying to solve, the preconditions and postconditions and so forth. And it should use that to essentially search through the actual problem solver's using the problem solver's algorithm, a set of appropriate actions to be able to be taken given these constraints. Now, The description that was provided by Dr. Norvig, at least the implementations that we're going to be covering today, a lot of which are available at his GitHub repo. And for folks who are following along with us, I'm going to be posting this again in the YouTube description. But if you want to look at these ahead of time, I believe it is PAIP-Lisp is where his repositories are located. Give me just 1 second. I'm just confirming that. Yes. So if you go to this URL, you should be able to actually go and grab the code examples that we're going to be covering today. Um, the approach that he presents in this book is kind of twofold. He gives two different versions, actually, I think three different versions if you actually look at the code, and we're going to be touching base on that. And the idea is he wanted to kind of illustrate what he would consider to be the 5 stages of developing a program. Now, for those of us who are, seasoned developers and seasoned software engineers, some of this is probably already review for you. If not, just things may have changed, and the order in which you might do things may depend on, what you are trying to accomplish necessarily. But essentially, the idea about describing the problem in vague terms and algorithmic terms, and then implementing the problem and testing and so forth, is all stuff that we do almost in second nature when we are writing our programs and stuff. And as he approached the general problem solver, that's precisely what um, Dr. Norvig actually attempts when he's uh, writing out each of the like conditions and stuff that would allow him to actually continue program development. Couple things that I wanted to kind of bring up, one of which is his use of alias functions on top of the standard common Lisp functions. Now, for those who are more inclined to leverage standard library functions without proper aliasing, um, at least from looking at the examples, it will become abundantly clear that sometimes it might be necessary to create that alias function. Not so much in that it will make things faster or more efficient, but it will definitely make the program intent in its solution description clearer for the reader at hand. And we'll see an example of this, especially when we cover the first and second versions of GPS, particularly in the notion of finding all solutions and actions for a particular operator. Now, this is something that I did not cover last week when we did our review, but the algorithm that he ended up actually leveraging inside find all and find all if is actually covered in chapter 3 for folks who wants to go back and actually review what he actually implemented it. But I will give you an idea, kind of a brute force way of doing this without actually going through that much trouble, mainly because of the fact that since we have the power of the common Lisp library and the ability to actually reassign symbol functions to other symbol functions, it makes us, well, not even reassign, it's more assign, um, because we're going to point to uh, a function pointer in memory with a different symbol than what was previously provided. It'll make you accomplish the same tasks that he mentions in the book easier, but of course, if you want to write your own from scratch, you could certainly do so just because uh, Common Lisp gives you that ability to actually go and do this. Another thing that I wanted to kind of bring up is somewhat the importance of this GPS, just because it is, although the general problem solver, and I'm going to use general problem solver for the fact that nowadays GPS also means global positioning system, and most people who are going to look at this, they're going to be wondering, what am I talking about? The program was the first one to actually separate. There's two innovations here. One is, although he doesn't, Dr. Norvig doesn't explicitly call this out, he says that he's going to be covering this later. This is what he means. There is a separation of and encoding of knowledge, okay, in the system, in the system, and the problem strategy, okay, the actual strategy of solving the problem is a completely separate is completely separated from the actual knowledge base itself. We'll call it knowledge base for lack of because that is what it is technically. But in the book, you will see that he doesn't really explicitly call it that, just because we haven't covered knowledge representations and information, which he didn't want to go down deep into that rabbit hole, because information representation itself is a whole field. And it actually even includes a lot of the stuff that you see in modern AI programming, especially when you start talking about encoding results, inference results coming from, say, a learned agent and even a trained agent. Um, Additionally, since this was groundbreaking in the fact that this was one of the first implementations of such a system, it enabled a lot more research into the general area of problem solving slash planning. Okay, I say planning because in some of the literature, the same issue of general problem solving falls into that category of planning and planning strategies. So it's kind of the same sort of um, um, a relatively same area of actually doing research in. Um, the algorithm that they talk about, although we're not going to explicitly uh, deal with the specific algorithm itself here, is something called means ends analysis. Okay, means ends analysis is not talking about arithmetic means or geometric means in the mathematical sense, but it's talking about means in the linguistic sense. Okay, so a means to an end. All right, there's a some sort of goal in mind, and there's a certain set of things or means that you need to accomplish in order to get to that end or goal state. Okay, this notion of this analysis comes from two particular pieces of literature that I encourage you to read in your free time. That the author mentions, and I know for some of you who have read this material, this might sound like a quick review, but some people tend to gloss some of these things, and these philosophical pieces of I feel is something that is underappreciated, even in the field today, mainly because of the fact that a lot of times we're looking at the goals, and we're not necessarily seeing the forest from the trees. And oftentimes, when we talk about AI and we talk about implementing these kinds of systems, understanding the philosophical implications, particularly when you start talking about task management and task completion, become important to know where you want to necessarily draw the line from a completely automated system into a semi-automated system. Mainly, if anything, you get as far as you can, but also understand that at some point, bringing in a human into the equation might be useful. All right. Um, Time and time again, we see that a lot of tasks that we end up automating tend to be tasks um, that are relatively easy in nature in terms of their completion, and they're so what's the word, routine, that it's much easier to actually um, remove the human out and then just have somebody do it with consistent results all the time. But as you go higher and higher level into a lot of these design systems and stuff, it becomes more of a objective issue and into more of a subjective area. And a lot of these means analysis and these philosophical papers about intelligence then will fall into that category on how to make a coexistence type system that allows people to essentially become superhumans, okay, without them evolving, because we now have a coexistence with the technology that we're adopting. So the two papers that I wanted to bring up that this was mentioned in the book that I thought might be useful for folks to check out. I haven't had a chance to actually really dig into both of these. I just really briefly tried to see if I could grab a copy of them. Is Newell Simon's general book called Human Problem Solving, which they go and cognitively look at the issue of just how humans actually tend to solve problems. Um, the other one is actually something more classical in terms of philosophy, and that is Nicomachean Ethics by Aristotle. And that I'm sure you could probably find somewhere in your local library. Um, it is a pretty nice paper that I think it's actually a book on how ethics are actually done. And there's an issue on means to an end analysis in there. In fact, the book actually quotes Aristotle, if I remember correctly, somewhere in there to talk about how it approaches to this means end analysis. Um, so rather than actually trying to implement the strips implementation, which is what we were covering in this book from scratch, we're just going to go and do some code review today of Norvig's solutions on from his repository, which gives us an idea on what he was thinking on how this is kind of implemented, and we could obviously try and improve some of this stuff with you know places where I would have probably leveraged a more object-oriented approach versus a um, just using def struct, but that's just me. Um, at the time that when I was reading this, in fact, and I was trying to implement it from scratch, I was attempting to use classes and class-based analysis, and then I realized, oh, this can be simply implemented using a struct itself too as well, like what Norvig ended up doing. And when I saw the solution, I was like, okay, I see how this is useful in this case. I'm wondering when you may end up find it more beneficial to use, say, a def method versus actually version than actually using the def struct version. Um, so before we begin on this, as normal, I wanted to bring up for anybody, uh, I wanted to kind of bring in this just a couple of things. One, as usual, this is a free for all kind of book club. If there are people who have comments and questions, feel free to post it in the Jitsi stream and or the chat, and I will address them as I see the questions. Um, Thanks to our folks from looks like we have an Albuquerque resident who is watching these streams. So, hello from Albuquerque. Thank you for joining us along, and it's it's great to see folks from the New Mexico area. Um, so I'm hoping you guys like the material as we go on. Um, so I think to begin with, before we look at the code, there's a couple of things that I wanted to kind of touch base on. One is throughout the book and the chapter itself, it became abundantly clear that with that, the one thing that general problem solving was essentially trying to encode in terms of the algorithm, because the algorithm is actually pretty simple. It's literally nothing more than when we look at the code is do we achieve this goal? If we haven't achieved it, um, and achieved it means the goal is inside the current state of any environment, and I'll define these terms pretty pretty soon. Otherwise, we return. Otherwise, we go and search and look at all the possible goals that conditions that we can actually accomplish to lead us to a situation where we could actually accomplish the goal itself in task. And there's a couple of things in here that uh, were brought up. One is the current state of the world. Okay, the goal state. Where do we want to be? Okay, and then something that he calls an operator. Okay, the list of operators. Okay, in fact GPS itself, and using Lisp like notation, GPS basically looks like this. We take the current state, the goal state, and the list of operators, and we essentially check as we go and say when every goal has been achieved in the goal state, then we say the problem is solved. Otherwise, we then look for a way to actually, in through the list of appropriate operators inside the Lisp operators and things, whether or not we can actually go and find a path effectively to get us to the goal. Okay, and that's essentially what GPS is. It checks to see if whether every member in the goal has been achieved has been achieved, or if there is some representative operator that we can apply that will get us to the goal. We could then move on with the general problem solver and actually execute this. A couple things about the operators that I think is also something that was pretty important to understand, and that is operators are essentially uh, they're essentially nothing more than, and let me just go ahead and put it up here. They're a list of a couple of things. One is an action that can be taken on the world. Okay, that's essentially the name of the action that you're trying to apply, the operator that you're trying to apply. Okay, the list of preconditions. Okay, so what preconditions have to be satisfied in order for this operator to be applied? Okay, and a list of effects. Okay, now the list of effects, the way the current knowledge representation in the implementation deals with, uh, involves actually really enabling and deleting operators that were previously satisfied or not satisfiable inside of the current state. This allows the search to essentially look at all the actions as it keeps on going through the list, to be able to uh, see if we can actually accomplish the goal. Now, the question now becomes, when we look at these operators, okay, what is considered to be an appropriate operator? Because an appropriate operator is essentially nothing more than something that can be applied on. Okay, and we already covered this earlier. Is that if the goal is in the operators list, okay, it's one of the effects that's inside of the list, or if there's an approach to actually to take one of the effects in the list, then it can be considered to be an appropriate operator. Otherwise, it's not an appropriate operator because there's no path to the goal through the list of operators that we currently have. And the way we implement this is through essentially writing a predicate to essentially check to see if there is a path from the current operator to the goal state. Okay, to the goal operator that we actually are trying to solve. So in our example that we were talking about earlier in the book, they were talking about Sun at home. Is there a path to Sun at school through some of the list of operators that we provided? If there is, then we will keep on moving. Otherwise, we'll treat the problem as unsolved. Okay. So with this, we can start looking at the first kind of version of um, GPS, um, and I think it's anytime anybody has questions, feel free to drop a line as I go through this. 1 second, I'm just checking to see if there's any. Okay, so let's look at the first version. Go to PAIP Lisp. Oops, I can't. PAIP Lisp. Okay, and go into Lisp 1, and let's go to GPS. I think it's, oh, actually, this is the final version that he covers. This one. Okay. All right. So an initial version that was brought up to this, and I'll be honest with you, when I looked at this for the first time, I was like, why the heck would we do it write it this way? And it's because you have to look at the context in which this first version is written compared to what the second version is, because most of us who are familiar with Common Lisp will end up choosing and going towards the second version, which we'll cover in a second, and use of a different approach. But this is kind of what a naive approach would be, which is you have two global variables, one that represents the current state of the world, which we'll just simply call state, another one that's a list of the of available operators, where an operator is your action name. Okay, that's a symbol. Your list of preconditions, your what operators are you adding to the to a potential state list, and what operators are you going to be deleting as a result of actually acting on this particular operator. Okay, and so what we would then do is we can write essentially GPS has the following, which is nothing more than um, if every goal in the list of goals that we provide, and again, you see GPS taking the current state, goals, and operators, and in this one, we treat the current state as the list of operators defined by the global variable, as well as the list of operators is also defined by the global variable for ops. If every one of those goals in that goal state is achieved, then we could just treat the issue as solved. Otherwise, it returns nil effectively when the if none of these are satisfied. If they essentially it's impossible if there isn't any path search that would be available for a person to satisfy this list. Um, so what is achieved is probably important, and we were talking about that earlier too about operators. And a goal is achieved either trivially, it is a member of the state, or like I said before, we find all goals and we figure out a path such that we can apply the operator um, to that given set of goal operators that we found and see if we can actually reach the goal there too as well. And as you see, as we go through the search, find all will become important because that's essentially trying to figure out um, how we are going to actually figure out what operators to actually apply. Two other things that we're going to probably cover too that we need to is what is considered an appropriate operator. Like I said, the appropriate operator is nothing more than checking to see, in this case, we're going to use an existence check. This is the easiest way to actually handle representations. Now, naturally, for more complex problem domains, it will be it's obvious that this is somewhat of a trivial representation of what would be considered to be a goal. We touch base on that a little bit later about limitations about this version and even the second version in many respects. But for our current case study example, this actually works quite well from at least the test cases that were brought up in the book. Um, So the next thing is talking about updating the state, because when we're applying an operator, we're effectively updating the current state because we've taken an action. And when you take an action, some effects have to occur. In this case, what we're going to do is remove a set of operators that we've actually have in the current state, and we're going to add an additional set of operators for whatever's remaining to see if we've actually reached that goal state. Okay. So first things first, we need to check to see if all preconditions for a given operator have been achieved. Okay, this is very important because of the fact that these preconditions become useful from a cognitive standpoint. So when you're defining your operator, and you know that those operators have certain constraints that need to be satisfied before that operator gets executed, those are your preconditions that need to actually be checked ahead of time. So thanks to the every operator, and I'm sure everybody has seen this. This is just a predicate. Every basically runs through your list of preconditions and calls achieve on them, it will then execute that current operation because we've now says, okay, this operator is now a viable operator to apply. And all it does is here in this case, we're saying that we're executing it. We're taking the operators that and this is effectively what an effect is. Okay, we're removing whatever is uh, in the current state that represents operators that have not been executed on. So when you look at the delete list, this is A, not B. Okay, this is very important because the order matters. It's not um, when you look at describe set difference. I had to make sure that this is the case. It essentially the ordering of how you specify the list is going to give you different results. So make sure that the one that you're trying to get the set difference on, so A not in B, is, A ends up being the first set, or in this case list that is representative, and then you provide B. One thing also to mention, you may also have noticed we are calling the set difference, but we're acting on lists. Technically, as far as I know, even now, unless you're using a third-party library, just a reminder, as far as I know, sets aren't actually a native data structure inside Common Lisp. List and vectors are, they're both sequence types, but sets do not exist. There's list, vectors, hash tables, and uh, list, vectors, hash tables, and I think that's it in terms of your collection types for the three. I might be missing one more there, but those are your main three. The ones that I've actually dealt with. Oh, concells if you're going to dotted pairs, which some folks may say, well, that's a list, and you can actually do like vector dotted pairs if you really wanted to, although I wouldn't necessarily say that that's a great idea. But dotted pairs are also there, which is car and cutter, so you could treat them as individual cells. The set operations, unit operations also will work on then sequence types because of this. So you can use, if you actually look at set difference, I believe set difference doesn't explicitly, no, I think set difference also only works on lists. That's the other thing. There's a couple of algorithms that work on all sequence types. Because lists and vectors are both subclasses of the top level sequence type, but there's a couple of algorithms that have not been updated that also has that ability. This shows actually the the evolution of the actual CL library as we go through this. So apply operating actually just runs these set operations and gives us essentially a new set of operators that we may need to achieve on before we reach a goal. This should give you the intuition very quickly that GPS is all it's doing. It's doing a search. Okay, can we find an algorithm to actually do this? Um, so now, okay, there was a question about which book are we talking about. Yeah, so just to repeat, the book we're covering is Paradigms of Artificial Intelligence Programming, Case Studies in Common Lisp by Peter Norvig. Um, Anybody? Yes, another comment about my setup. Yes, I am a Roswell user. I'm a big fan of Roswell. Probably the best thing that happened on top of Quick Lisp, honestly, for Lisp management, and it helps, especially if you're trying to experiment and run with different Lisps when you are writing a general purpose library. Other questions? And I don't quite understand the comment about ER, but that's okay. All right. Okay. So let's run this example. Okay, we have a knowledge base here that Dr. Norvig encoded from the book on how to drive your son to school. Okay, and what I'm just going to do is I'm just going to load this guy into my Lisp image here. Let me first actually probably, hopefully this doesn't mess anything up. 1 second. Looks like my key bindings got messed up again. Okay. Okay. Okay, let's do this first. Okay, let's load this guy, see what happens. Oh, okay. Let me do this. Looks like I had something redefined here. Let me just quickly do that. There we go. Okay, so we now have everything loaded. Excellent. All right. So now, oh, I forgot. We have to talk about find all. So, like I mentioned earlier, find all is an important piece of this piece, which is actually trying to find all goals associated in this list of ops given this testing um, given a test um, given a test function. Now, one thing that this does not use that I think I should provide here is Alexandria, because I don't really want to rewrite some stuff that's already in Alexandria. How do we go and implement find all? Well, find all actually is nothing more than, it can be written two ways. Okay, the first one that I tried to do is try to do it on the fly, which is try to attempt to use mapcar, um, and check to see if we have a predicate instead of a function that maps across each list, so that we could actually spit out what is in and not in the list. But a better approach actually is if we erase what doesn't satisfy the function, because then what that leaves us is actually dissolutions it that are actually appropriate. Okay, so to implement this, what we could do is very quickly, and I'm not going to modify this particular code because I know Git's going to start complaining about me not doing this. I'm just going to go ahead and write this in my buffer. We could write find all using the following like function signature. Now I'm going to grab the function signature that's available to us in um, the book, which is, it takes an item, a sequence, okay, and then we grab the rest as keyword arguments, keyword args, okay, and then additionally we provide two mentioned things. One is a default function a test function that we're going to use, and we're going to use EQL for this appropriate thing. Um, you can use whatever you ideally want, but there are different equal operators, and they do mean stuff. So I think at some point we've discussed this, but just to review, we have EQ, we have EQL, and we have equal, and each of them provide a general. There is a difference between those three. So like if I remember correctly, EQ is dealing with the cons of it. EQL looks at so EQ makes sure that two things are pointing to the same, I think, allocation in memory. EQL is the more general version of that. It doesn't necessarily mean they're the exact same location in memory, but they have to be essentially the same object. And equal is what we would consider to be like dot equal in other languages, or the equals equal sign, which is where essentially implementing operator equal. We're actually looking at content inside the representation of the function. So if two things are equal, there will be equal, but they may not be EQL, and they may definitely not be EQ. Um, I recommend you looking at the hyperspec for more details about that. But um, okay, so there's a question here. These GPS techniques work with a real set implementation, like from fset and exit. Yes. So there is a question about GPS updating GPS to leverage a set implementation like fset and Alexandria. Yes, from a standpoint of implementation, definitely you can use fset or Alexandria pretty easily, and just replace a lot of the stuff that you can do in the GPS implementation with that native set implementation, and the code will become, I think most of the code will just work. Um, the one thing that I will say that you may need to change is set difference might require for fset, I believe actually, the set different function call is different. I don't think you can call set difference itself generically. It's not a generic function for fset. So if you're using fset or Alexandria and using their base set implementations, you can certainly do so. I'm using Alexandria here mainly because Alexandria already provides us with a complement method, which let me just show you here by opening up. Hold on one second. Here, space sly scratch, and do this. If I remember correctly, Alexandria has a complement function here. Complement. Oh wait, was that in Serapium? That may have been in Serapium. Hold on one second. Let me grab this. Okay, now I do this. Click load. Because I really didn't want to kind of, I mean, you can easily write a complement function. It's just that why implement something that's already available to you. Um, okay. Serapium. Interesting. Looks like they took it out. Comment, comment. Compose. Oh, it has compose, but not complement. Okay. So we need set complement. So we're going to have to write complement as well. Okay. So the first thing we need to do is quickly write complement. And what complement is nothing more than it returns a lambda that takes in the rest of its function as arguments, and all we're doing is we're just applying the function to the arguments. Actually, we need to find apply fung args and then take the not of this result, and that's it. There are other ways of implementing this, but this is the simplest one that you could do. 1 second. What is it complaining about? Combination. Wow. Huh. 1 second. Ooh, there is a complement function. Where is this defined? Ooh. Okay. I didn't realize that there was one. Okay. So that makes my life easier. Should have done an apropos before I actually looked at this. Let me just do one thing before we continue. Okay, let me just check one more time. apropos complement. Okay, complement of, let's just check something, even p. Okay, and what we can do is, let's do this and just see. Oh, it doesn't allow me to do that. I have to do a func call of this guy. There we go. Okay, so this actually works. All right, so we don't need to actually write the complement function. It's actually available to us, but what I showed earlier, this thing actually is basically what complement can look like. For find all though, given this implementation, oh, one more. Let me do test not, and then allow other keys. This is basically the full signature of what find does. And find all essentially matches essentially what every common Lisp API find, whether it be find if, remove if not, find if, and so find if not, and so forth. All the variations essentially leverages the kind of the same API signature. But what this does is essentially write this very simple thing. We could do if test not, we can do this, and then we just apply. So if test not actually exists, we apply test not against the complement itself, and we basically call remove on our the item with the sequence. Okay. And what we'll do is we're going to pass the test not function to be the complement of our test not function. So the predicate that we provide, and then the keyword arguments. And the reason why you write it this way is because for folks who are curious, it's because what we're trying to do is we're trying to find all solutions in a particular. If we, just to give you how this would work, hold on, sorry, for some reason. There we go. Hold on, let me just kind of finish this. It's because what remove does is the following. Okay, let's just show you what remove does very quickly. Let's say you have a sequence and you do remove in the typical sense 1, 1, 2, 3. Okay. You see you'll get 2, 3, but if what we're doing is find all with, what we actually want isn't necessarily one to be removed. We want one to be filtered out. So you need to essentially remove the complement of this. So stuff that is not one would end up having to be removed. 1 second here. Okay, it's having some mic trouble. So to actually do this is you do remove 1, 1, 1, 2, 3, and what you do is you can do test not, and then provide a lambda x and say equals 1. Okay, so 3. Hold on 1 second. I may have done this wrong here. Invalid arguments 2. So it'll be XY because of the fact that it's taking two arguments. Um, and we basically need to check if X equals Y. Okay, and then that's it. Okay. Um, Now, what's interesting to note about this is we do have, by the way, a not equal. So you could have also written this with just a test function, um, and it will effectively do the same thing. Lambda xy. This is one of the little quirks about a lot of these APIs. They do have both situations, but effectively they also have both operators too as well. So if you really wanted to, you could effectively implement it in two different ways. In this case, what we're doing is we're using test not if it's defined and test if it's defined. So remove item sequence. Thank you. And test complement test keyword arguments. Okay, there we go. Now, one thing to also point out that I think is important is for the keen eye and the more, uh, um, I guess you could say more intermediate common Lisp programmer, this test not and test for remove is also available to you if you use remove if or remove if not. Okay, so we have a remove if not as well that can essentially implement that too for you. And it gives you basically the same signature, except the predicate is going to be automatically complemented, and you can actually leverage this, which I thought was more representative of what the algorithm is trying to do. So you could have just simply done also if you really wanted to. Although I don't know whether this is kosher or not. Some folks may say it's not. I don't know. If you wanted to, you could make. I'm just going to make a function called um, find all r to kind of illustrate this. You could also do set f symbol function, and we actually define symbol function here. Okay, and find all r. Okay, and then just remove or add this to um, attach symbol function to remove if not, and this essentially would end up doing essentially the same thing that we saw earlier. So if we do this, find all r now becomes an alias to remove if not in the same signature. So this also is possible if you know what if you know what is available to make your code cleaner. The point is for folks who are on the stream, is my audio better? Um, okay, so let's move on. So given this common implementation, what we just did, um, and what we just loaded, we could actually run um, a basic example of the GPS. Setf start state to being, let's say, sun at home, and it is, if I remember correctly, sun at home, car works. Okay, and now undefined variable. Hold on a second. Oh, right, right, right. Okay, undefined functions apply up. Oh, that's already defined. Okay, let's go ahead and run this again. Okay, so now let's go and say GPS state is our that. Let's say that we want sun at school, and let's take our school ops as our operations. You could see that we could quickly get to um, executing drive sun at school. Okay, we can also try, let's say that we change the state to being needs battery and have money. Okay, you could see then when we try running this, there's actually no way of that's implement interesting for us to actually get to um, ah and that's because we have money, but we don't have some ability to contact. We don't know. We may not know who the shopkeeper is that actually can install our battery. So we need to also have some sort of phone book. This was designed at. Remember, this shows how dated it is. We could have also used Google, and this hasn't been modernized. You can see now that when we run have phone book, um, this gives us the uh, a solution given that knowledge space um, to actually run GPS and get us to the ultimate goal of driving the sun to school and getting the sun at school. Please hold on. For some reason, I'm getting just a brief echo here that I'm just gonna just try to quickly solve here on my end. Okay. All right. So let's take a look at the questions so far that we're covering here. Question one. Oh, is there some graph algorithm happening behind? So funny thing, this is at a high level, you could think of it that way. There is a graph algorithm occurring, but it's not actually implemented. It can be looked at as a graph, and you could definitely look at this as a graph walking algorithm. But the actual code itself is not leveraging. I guess you could say that it's leveraging one representative graph because of some apply operations here. Um, but it's not an explicit graph algorithm that's being written. It's not, we're doing effectively like um, a uh, a breadth first search. Okay, um, we're taking whatever's popped off at the current state has an operator to see if we reached a goal, and we're applying it if it's achievable because it's looking through that operator as you could see with the apply um, op that we're looking at all the preconditions in the and you could think of these preconditions as the frontier of the actual goal itself, and if it's achievable then we'll actually go and execute it. But it's not an explicit defined graph algorithm, um, but it is conceptually a graph algorithm that's been implemented. It's not explicit in the code though the way it's implemented. I hope that makes sense. So you wouldn't know when looking at the code that what you're dealing with is a graph. When you look at the code as a whole, it is essentially a graph. So this is all great, but there's a couple of problems that this current implementation was um, this current implementation has. All right, um, and for folks who read the book, I'm not going to repeat a lot of the stuff, the descriptions here, but effectively you have the running around the block problem where you can't necessarily figure out if you're since where you start is where you end. You don't know necessarily using the general problem solver whether what is actually the start state and what is the end state, and you may end up actually thinking that you're already at the end state and you're not. So so it wouldn't even it will you will end up running GPS and it'll say true even though it didn't actually do anything. The other stuff is also again because like one of our audience members actually mentioned rightfully, we are dealing essentially effectively with this conceptual graph, right? You have this notion of the clobbered what Norvig calls the clobbered sibling problem. Okay, you have essentially two solutions or two goals that can be satisfied, but they're siblings of each other. If you wrote this in a graph model, and depending upon which path gets executed first, one goal will get achieved and the other will not, because you've clobbered any possibility of actually being able to accomplish that second goal. So the example that he provides to illustrate this clobbered sibling problem is pretty useful to look at. Um, let's go back to our original state. Let's make sure our state is still um, have money and have phone book here. Okay, right? And let's say that instead of son at school, we also want to have money. All right. Now, in one place, we look up the phone number, we look up the telephone shop, we give the shop the money, and we said we go and drive the son to school, and it's solved. But if you went and ran this by changing the order, you'll still end up getting the same goal. And in both cases, what's happening is you're technically losing money because you're giving the money to the shop, right? So this is kind of they um, what he means by the the clobbered sibling problem, because you're always eating up the money. They're siblings of each other. Currently, the way GPS is interpreting them. Now, have money doesn't necessarily mean you're not going to spend some of it available. Just letting you know. This is just for a simple example. It's a binary. You have money, now you don't have money because you've given the money away. Okay. One way of dealing with this is dealing with creating a general algorithm called achieve all that checks to see if the goals are a subset of the actual current state, but um, that could also potentially be problematic. And the reason why is and the reason why, if you look at this, have money is necessary to actually drive son to school when you have car needs battery, right? But have money is now eaten up and removed when you actually set this up in a graph model. So this ends up causing stuff. And if you use the subset approach, it will recognize that and say that the problem's not solvable because these are siblings. You're going to eat up one by trying to accomplish the other. Um, there's also the other one about um, uh, this also brings up the what he calls the leaping before you look problem, which is basically um, another way of addressing this clobbering siblings problem that he brings up. But again, um, planning and execution of these strategies, especially when you're dealing with these siblings, are interleaved, and there becomes this situation: is are you going to take one path or the other? You have a binary decision that you have to make, and this is something that I can't um, uh, undersell as being a problem with how you design some of these stuff. And this is not just specific to GPS and this implementation. There is some workarounds in this that we'll see in the second version of this, but it is something that I'll bring up just merely because of the fact that in other problem-solving situations, when you have it in this strict binary sense and you represented your knowledge in such a way that you have to do one or the other, you could hit the situation where you need to make a decision, has to pick one versus the other, and not have both. So, but GPS's goal is not to deal with that. It's trying to solve both problems and leave us with this end state. And for that particular goal, we end up recognizing that there's a limitation with this particular implementation. Um, the main problem with this is also related to the lack of what we would consider to be an intermediate information representation for a particular solution that they may have found. Let's say that when GPS tries to find a solution with this particular representation that we showed in mind. If it can't find one, we already know what it's going to do. It's going to return nil. But that's problematic in some cases because of the fact that uh, there may have been a situation where we expected a solution, it returns nil, and we have no idea why that occurs. So you can use debug utilities that's available to you inside Common Lisp to address some of this stuff. But this notion of having an intermediate information problem becomes more and more important as we address and attack more complex problem domains. I won't talk about debug too much here, just because I'm sure many of you have played around with the debug utility at some point. But if you haven't, just to show you just what this is, it's kind of like format essentially. Hold on one second. There we go. DBG. 1 second. I think it may have been debug. I thought debug was also available to you here. I looked at it last. 1 second. Optimization quality, policy quality. Okay, that's turning on debug. Let me see if debug IO is available. So debug IO is available. This is essentially for folks who are looking at this. Debug IO is effectively the stream to standard error, just like standard out and standard input. Um, Debug IDs are also available to debug DBG. No. Debug retable. Interesting. Hold on a second. Let me go here. Do this. Debug. 1 second. I think because we called debug earlier. Give me a second. I'm gonna be just trying one more thing here. Okay, there we go. And can use first line debug IO format. No, not that. One second here. What did I miss here? Oh, right. Thought there was something here. Okay, hold on 1 second. Let me see what is available in debug. Up the debug command, debug line hooks. We can actually set up the debug commands. There were some commands that I'm just looking up that I thought I was getting errors when I was testing this out earlier, but it looks like it was because of my own typos in my Lisp image, which is why periodically you'd want to play around with a different Lisp image than your current one that you've been running for weeks. um, 1 second. Da, 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 da. Looks like this. Do this down to no. Get it down to here we go. Kernel debug block. Okay. So we're gonna have to write our own ones. So there are a couple utility functions inside the book that they mention called DBG and stuff that you may end up having to implement that you can leverage to essentially do this. But all it is it's using format to actually go and create debug stuff into the debug stream. I'm not going to go and cover specific implementations of this just mainly because it's actually completely a tangent to the actual essence of the chapter, which is the uh, general problem solver. But folks who are curious as to some of the stuff that's in it, by all means, there it's on what's it? I refer you to page, I believe it's 144, 145 of the book for dealing with debuggers. and essentially writing debug output. So you have control over essentially whether or not you have turned on debugs or not, and you can leverage certain identifiers to actually be able to get logs for particular debugs when you're actually looking at some of the limitations and issues. Okay, let's move on. So given the four problems that we talked about, okay, running around the block, prerequisite cobblers, the siblings, um, what he calls the recursive subgoal problem, and recursive subgoal problem again has a review is essentially um, suppose you have a uh, a state where you don't necessarily have kind of a base case, all right? Like an example is let's say that in the school example, the book brings up about looking up a number in the phone book. And suppose you want to add um, finding out a phone number by asking somebody as well. What ends up happening is if you make this new, if you just push, for example, this issue of, let's say, push make op this action ask phone number with the preconditions as being um, in communication uh, in communication with shop, okay, and the add list has essentially sorry, the add list has essentially now you know the phone number, okay, something like this, and we add this to our school operations, okay. So now if we try to run GPS on um, the state where we have son at home, oops, son at home, car needs battery, oops, sorry, I forgot to specify the full problem, um, and have money, and we say son at school is our goal, son at school is our goal, and we take our school ops, you'll end up hitting this situation where we throw we get a trap and we have an issue, and what happens is oh sorry, I forgot to also include our implementation of find all. Okay, we try running this, we end up getting essentially a recursive call that that exhausted, okay, it's because, and what's happening is it's because of the sub goal that is occurring put us in this effectively an infinite loop, okay, and um, so to show this I'm going to just go and say trace the achieve function, okay, and we run this again, you'll end up seeing that okay, achieve kind of went through this non-local thing, but that's because of the fact that I just aborted the evaluation. Um, Let me do this again. Clear REPL. Okay, now let's run this again. And before I actually move this, let's go up here And let's look at this. You can see very quickly what happened is we hit this situation where we need the battery. We know we have money, so we told the shop that it knows the problem. We say that's in communicator shop, and now we achieved no number. But the reason why it's failing here is because if you saw the goal for the sub goal for uh, in communication with shop, sorry, not in communication with shop, with our newly added ask phone number, it's actually not removing anything um, from this piece, and it ends up adding something that uh, occurs recursively because it's going back, and we're always talking to the shop, but we're not actually moving from the shop itself. And this is a very simple call, but it's a nested call that ended up, blowing up the stack um, as a result. This is what Newell and Simon talks about for what they call oscillating among ends, and trying to figure out the means to perform them. So for a particular task, it might be such that we are in and in this particular example, we're seeing that we're oscillating between communicating with the shop and grabbing the shop's phone number. And the reasoning behind this particular thing is we're telling the shop that we want what the problem is with our car, and particularly with the bag. And this requires that we need to communicate with them. But one way to communicate with them is through the phone. But since we don't have the phone number, we look up the phone number, and now we have this situation where, oh, we're constantly kind of adding to no phone number, and ask phone number, and in communication, we don't actually remove the actual task of doing this. So it ends up deliberating with the shop about what the problem is. It doesn't actually give us anything. So what can we do about this? Well, let's look at the second approach to actually um, implementing this. Um, oops, sorry. Okay. Let me just close this out for a second, and then go here and load GPS. I think it's this one. Yes. Okay. So there's a bunch of new things that we now added, that was now added to this. One is a couple of functions related to whether or not we're executing a particular operator, whether or not that operator starts with uh, an executing convention. And the reason why we did this, this is done, is this new version of GPS that Norvig wrote was a it generalizes the actual representation of the action from what's actually being acted upon. Okay, so if you saw son at school, this created what in expert system folks would talk to you about are called predicates. Okay, and they're more actually they're not predicates. They're propositions. Okay, um, he's writing observations at is in a form that's generalizable to allow he use the same operator on multiple pieces of data. Okay, so you'll see in our action thing later on just how this will look like. Okay, and what he wrote is also um, some conversion operations that are necessary to make operators obey this kind of new convention that we want this generalized. So this way you don't necessarily need to change your database. We just have a new operator that will deal with this, okay? I will give you an example of this very quickly before we go and cover the rest of this. I think it's further down here. Where is it? It's not banana operations. It's the school operation stuff. Okay, so we need to actually load up the school operators in here. Okay, so we already have it, but we could certainly leverage it as part of this later on. Do this. Okay, 1 second. Why is this always... Okay. Okay, so let's load this version into our system. Requires. Okay, so we need to go and look at what is requires GPS. Oh, this actually changes because I think we need to do not requires, but require. Okay, let's do that. Don't know how to require GPS 1. Um, mm, oh, it's because it's not part of the central registry. Right. Let me just see what one thing. Did we provide a requires somewhere? Okay, so one way to handle this is, since I already actually loaded this, I don't think this is something that I'll deal with at a later time. Um, because this is actually not needed for us actually to talk about. I'll just comment it out like that. Okay. All right. Let's do this. Load. And what else is there? Append. What is append? What is he doing append on? Okay. Append. What was append? Append was mapcan on the function. Yeah. Right. So we call apply. So let me just quickly write this function because this is a helper function that he wrote in his algorithm. Defun append. This is just calling map car on the list and then appending the results. So we do this to list, then we do apply. We could also do reduce, but I'll do apply. Append on the map car of function on the list. Remember correctly. Okay, good. Load. Let's see. 2 dbg indent. Okay. So looks like he uses his debug utilities. So let me just go ahead, write up the debug utilities for this particular piece. Let me see. Actually, you know what? I don't think we need to use this, but we will see. Oops, sorry. I really didn't. we can cover the debug stuff in a little bit, but I want to first cover the main pieces of this particular thing, um, particular program itself, because that's very important for us to cover. Um, and then we could start adding to debugging some of this stuff. Do this, load, okay, and then find all if. Find all if find all if is just ah yes, find all if is just remove if not. F symbol functions. He's using the same approach that I tend to do. Okay. Remove if not. And before we move forward, we need to go and make sure that this is actually a symbol. Now we can do that. Find all if is the predicate. Okay, good. Okay, now we have a fully functional version of this guy. Okay, let's go in and run this example to make sure that we've solved some of this stuff, and then we will review the code, shall we? Just so that mainly I'm double checking to make sure that I didn't actually break anything when I commented some of the stuff out. Um, is the example that I wanted to cover. Okay, here we go. Let's do the GPS Sonnet School Home School Ops. DB debug intent. Hold on. Why is debug intent looking at? Okay. What this is the case, I need to go in and probably write. Go ahead and write very quickly. Defun. Where are the two? Because there are multiple locations of where this is being used, so we're gonna have to probably add these utilities just so that we can actually go through his code a little bit better. So debug IDs are the list of the IDs that we're creating, which is identifiers that are going to be used by debug. So let's go ahead and create that. Then you have def defun ID format string rest args. Okay, now we're going to attach a fresh line is basically a brand new line inside of our stream. We're going to attach that to debug IO. And for folks who've never seen fresh line, it's basically like new line or stood end line in C++. It's just creating a like a slash n. And then we apply format on the debug IO with the debug strings. Now we could probably directly call format here. We will change that in a second just to see if that makes any difference. But I'm just writing it out based on what I've seen in the utilities. Okay, in fact, let me see if this actually works, because I actually prefer that. Let me do this, do that. Good. What is the style warning? Shift G. ID is never used. Oh, right. Okay. When ID member ID and debug IDs. Okay. Now I'm going to set this guy to nil because this is an empty list. We got this working. Now let's quickly create debug indent and debug as well. Define debug IDs, rest IDs. And what this utility is basically creating, what we're essentially creating is, think of it like log4j and some of these things where we can attach a label to a particular stack, and then we're being able to attach more debug information to the stack. Some of these things are necessary when we're building more complex systems. For this simple example, it wasn't really necessary, but it looks like it's a lot of the code examples are polluted with some of these stuff, so we're adding some of these utilities for now. Okay, and then add that. Oops, did I accidentally? Oh, okay. So I can't necessarily use debug here. Let's just run debug instead, so we don't have any name collisions for the time being. All of our other stuff is not going to have name collisions, but some of these stuff, because they're part of the standard library, it becomes important to kind of recognize. Rest ID. Okay. Now setf debug IDs as being the if null IDs null, otherwise a set difference, because we're trying to remove some of these logs from our things. Debug IDs and IDs. Okay. Good. Run. Okay. Let's do this now. And add debug GPS for what we're attempting to do. Okay. And oops, sorry, I meant run debug. There we go. So now GPS is part of that member, and we can actually go and now run this guy here. Wait a second. Did I not implement debug? Oh, I forgot one more function, which is debug indent. Define debug indent. Okay, and what this is doing is, if we are actually debugging a particular member IDs, then add a fresh line, debug IO, Let's set up the indent of this. And this is nothing more just to add some spaces into debug IO. Okay. And we could run format debug IO format string args. Okay. Run one more time to load. Let's see what happens. Okay. This is what it will look like. Here is our debug situation. You could see that when we are what we are doing is we're looking up in the simple, and I guess a better example would be instead of this more complicated one, because this is the one that will actually hit us to the recursive subgoal problem. If we go back to just doing state sun at home, actually, you know what? It's probably better for me to do it this way. GPS sun at home, car works, sun at school, school ops. You could see that we've essentially started driving the sun to school. We planned it. We considered driving the sun to school. We achieved um, that the sun at home and sun at school. We see what achieved retrieved in this case. It says that we start sun at home and sun to school. And here, what this is going through is essentially each of the individual actions. Now, to really drive this home, because this is way too much noise, I am going to have to reload everything because it looks like the trace methodology is what's causing this issue. Give me a second here. We load our first version because this will give us our initial, and then we come here and we load our second goal. And now if we run this basic thing, we actually get what we expect. Oh, we also need to add two things. One is we need to add, where is it? Sut f symbol function this for find, and then we have a version of slice scratch, which has our final goal. Okay. Okay. Now we can actually run this. We did that. Okay. Do that. Do school ops. You can see that it's executing things pretty quickly. Let's go to the the more complicated one. Okay. We can see that it's nil, but why is it nil? Well, let's first turn on debug. Okay. And let's start the simple example. What happens when we do the sun at home? Well, here's the goal. We consider driving sun to school. We see sun at home. We see car works because we're trying to achieve those. And so we end up deciding to make drive sun to school. But let's see the other example, which is what the more complicated one, okay? Here we have essentially the goal of sun at school, so we need to drive sun to school. We look at the sub preconditions, okay, the two sub goals, if you will. Well, since a car needs a battery, we know we need to consider shop installing battery because its precondition says car needs a battery and shop knows about the problem. So you need to go through and communicate with the shop as you are going through it. And then what happens is you give the shop the money, it knows about the problem, and then the car works. Um, what's actually interesting about this is it looks like this one actually does not solve the second issue, which is Sound at School is still actually interpreting through this because it looks like it's actually still recursively communicating with the shop. Um, this is interesting. I'd have expected this to actually have figured out that this would work, but it didn't. There is something incorrect here. We're not going to go through the banana ops just yet, just for a second, for the sake of example. Here, let's see here, what is it? Oh, right. I think I might be using the wrong goals. Let me see here. Right. So let's go here and do use school ops. Okay. Let's see what happens here. Still has the phone book. It's unable to actually get go through and you see it's kind of in this kind of like loop. If phone book shop has money, gift shop money, have money, gift shop money, and so forth. It isn't actually going through the list the way I would have expected it to, but that's fine because this also illustrates some of the problems of it actually. Um, oh, there it is. That's probably what I need to do. I have to convert this guy. Shift G. Let's see what this does. Okay, so I'm going to have to add because it's in this infinite loop because it didn't get converted. So what I have to do is I have to do set ops. Give me a second. Where is use? I was surprised that use should have not. It it didn't grab this originally. Where is the use function? If I just fix that, will be in, I think good good goals. Um, where are you? Use. Here we go. Um, okay, so what I'm gonna have to do is do this. Um, oh wait, what am I doing? Just do this. There we go. And then do map C convert op school ops. So now if we look at ops now, we actually are using the new version. So if we then go call a simple example here, this should still work. which it does, then if we call the more complex example, you can see now, oh, it's still messed up. Okay, interesting. Why is that? Action add less have executing giving money. So this is actually not doing what we expect it to. Is it of the form? Is it start with executing? Does it convert that into... Okay, so so what this convert option does is unless there's already something existing there, it'll try and push a new action to that add list. So if there is already one that already had an execution, it will just run and execute it. Interesting. So that means this simple example would also be failing for the examples that were presented. Interesting. Okay, I'm going to keep an eye on this one. Let's see here. Okay, I see why. I missed one more thing in this example. Oops. Go here. Quit. Quit. Okay, no. Okay. Okay. I forgot in my start state that we also need have phone number, phone book, and then we'll see the execution. Okay, so it was me typing up the example incorrectly. So the plans are all working for the basic examples, as you can see here. Um, there isn't actually anything more spectacular about this. And what this new thing does is you can see that all the actions that it's attempting to do of the form of executing lookup number, executing telephone shop, and so forth. Um, this also fixes the issue that we were seeing before related to um, a couple things. One is it does no longer blows up like we saw with the have money um, problem. Doesn't actually say that doesn't it can't recursively solve or blow up the stack. Um, you can also add additional things here and see that it's unable to exit particular actions. Um, and it shows you that one of the two other goals are available, can be acted on, but not both of the goals can be acted on. So in this case, the collaborating siblings problems, in both situations, it just presents itself as, being unable to um, solve this problem. So if we just get rid of the GPS here, the debug, and we run this example here, you'll see that it can't solve that particular problem, whereas it's able to solve this one. Okay, it gives you a plan. This There are plenty of other domains that it covers. One of which I'm just going to quickly do, like new problem domain. Like if you're doing the monkey problem, actually the maze one is probably pretty interesting. Um, so we have other um, two problems inside of this test code. One of which is dealing with maze domains and figuring out a domain maze or path inside of a maze. And then the other one is dealing with a classic cognitive problem about a monkey climbing onto a chair to grab some bananas. So like if we try end up running the banana one, okay, and we just quickly say GPS at door, on floor, has the ball, and the monkey is hungry, and it sees a chair at the door, and its goal is to not be hungry. Okay, then it'll push the chair from the door to the middle room, and then it'll climb onto the chair, drop the ball, and then grab the banana. Um, Notice again, because it's a generalized code, this shouldn't surprise many of us who is reading this. The algorithm still acts the same. If we jump into the actual goal itself, we could see that we changed, and I think this is also important to take a look at. Let me see if I can get this side by side. What we did here in the naive version, we check to see if all the goals are achievable. Okay. Instead, what we've done is we tried to find all the actions, valid actions that are potentially achievable here. So this one becomes a search problem versus an actual satisfaction problem. And a lot of the examples that are brought up about the different problem domains also illustrates a different issue related to just in general artificial intelligence programming, whether you're talking about classical or modern day machine learning techniques being used. It's a lot of exploratory programming. It's a lot of experiments, devising your experiments, making sure that your experiments make logical sense before you go and encode those experiments in a way that can be executed by your agent. Okay, so you could treat this GPS as an agent that can take the state of the world, what the particular goals, and it's able to solve them as long as the encoding makes sense. And I think that's a very important thing to take away from this as we keep going through this. The goals related to um, these kind of basic AI programs are all based on a narrow-minded but general enough view of the world to do task completion. And I think that's something that is important to understand when you are going through some of these case studies, and as we keep on going through the book. Um, Even here, even though we're able to jump into different programs, uh, this version has limitations too. I'm just going to quickly show you an example of the maze domain, just so that we don't, you can, further see that this is general enough to actually handle even generic like path searching. So here we have, let's say we have, uh, so here we're gonna have to do, what is it? Oh, use maze ops. Okay, and then let's say that our goal is that we're at 1 and we want to be at 25. Okay, and you could see that it'll generate all the common goals for what represents a maze. Um, the maze that we saw here, the diagram is in the book, but this is a quick goal from 20 to 25, and is able to actually go and accomplish that from generating that maze. Now, um, the three limitations about this version is just like we had something called the leap before you look problem. There's also not looking after you don't leap, which is solutions that may end up taking although GPS is prevented from taking ill-advised actions, even with the repairs that we made to the program. The example, and I'm going to leave this as an exercise to the viewers to watch through this, just because this is a particularly fun thing to try out and and observe. It's even when there's a solution, GPS, the way it's currently written, this version here on our right side, still may not be able to find a solution to achieving all the goals for a given strategy, even though one is potentially possible. And the example that I will just, um, give from the school example is let's say that you want to have a taxi on the school. The example that they provide is a taxi at school and be able to drive the son to school versus driving the son home. And drive it creates this situation where essentially the decision is can be made that you could still drive the son to school if no options are possible, but the way the knowledge base is actually searched, um, if the action taxi son to school is there and it cannot be accomplished, it might be the situation where it ends up not, doing anything, and GPS gives you the wrong solution. Um, there are other domains related to the maze one, like lack of descriptive power, where you are dealing with essentially the ability to you have an issue with characterization on how the problem is actually described, and again, solutions are unable to be found. Um, and even though there is a way to actually go in and actually solve it. Um, this usually can be addressed by a change in information representation, but since this chapter doesn't talk about knowledge reps, I will not, talk about it any further. This also, the knowledge representation is also related to uh, assumption that we have perfect information about the domain that we're dealing with, but in reality, that is never the true. Um, you will never have perfect information and perfect observations, and so you have, you know, this world of trade-offs that GPS in its current incarnation, at least this particular example, is will definitely not cannot solve. Um, Finally, I think it's important to understand that most people, most agents, most real world agents are multi goal, satisfying agents. So they end up addressing and retrieving and dealing with multiple quote unquote knowledge bases of actions and appropriate, um, uh, what's it, appropriate preconditions and postconditions related to different, maybe orthogonal problem domains. And it is the job of the general problem solver to be able to address multiple goals at the same time. And currently, the way it's currently written, it's impossible to do so. Um, this all shows the basic limitations. And you might think, oh well, a naive person might think that this is doable, but as most of us now know, GPS was designed at a time where we didn't discover until much later that the entire notion of being able to get a theoretically correct program that solves and satisfies all the goals in a particular problem is MP hard. And there's a large number of problems that actually addressing this for those who've taken your run of the mill class in algorithms would have encountered. This is a pretty typical thing. And so, although general problem solver was a very lofty goal and enabled to address some of the more specific needs, the actual real goal of being a general problem solver was impossible to take on. It and they discovered that very, very quickly. Um, and so uh, GPS left itself as being a pretty simple, pretty focused program for doing task satisfaction. And if you're able to address your problems in a format such that you can essentially deal with it in a reasonable computational search, then this approach of creating this simple program becomes doable. And as you can see with the examples that we've seen, there are a class of problems that are complex enough that would be able to still be solved using GPS, albeit not all problems will be used with the GPS approach. So I didn't realize it'll take us this long to cover all of GPS, but next time, we're going to actually go through the exercises at the end of chapter 4. Um, so that way we can actually have some discussion about these. And for those of you who are still with me, I appreciate you guys taking time out of your Saturdays to watch the Common Lisp study group. If you like our material, please subscribe and hit the bell icon for subscription and like our videos so that other folks can actually enjoy it. We are going to keep on trudging along. We're going to also maybe talk a little bit about chapter 5 tomorrow, but chapter 5 next week, but I'd rather uh, do the programming problems and have some discussion first, and then work our way through um, the exercises and have some commentary on the exercises as we go through this. So, are there any final questions? Okay. Well, thanks everyone. I wish you all a good Saturday or Sunday or wherever you are, and have a great evening too. Bye.